Okay, now let's consider what happens for another whole class of instructions where the second operand doesn't come from the register file, but instead comes from the 16-bit constant encoded in the low order 16 bits of the instruction down here. So we're no longer treating these bits right up here as the RB field. We're actually using the entire low order 16 bits of the instruction as a 16-bit number. We have to convert that into a 32-bit number, right? And then we use this multiplexer here to choose whether the second operand into the ALU, the B operand in the ALU, comes from either the output of the register file or the 32-bit constant built from the instruction. Right, so in this case what we've done is we added a new control signal. You can see that on the next line of your diagram here. We've added the B cell control signal. And we've actually set it to 0 when we want to use the second operand from the register file. And we set it to 1 when we want the second operand to come as a 32-bit constant built from the instruction. So we've basically taken care of all but 5 or 6 instructions in the instruction set with this data path. This data path will get the job done. It can operate on 2 register operands or a register operand and a constant. Let me say a little bit about how we convert the 16-bit number into a 32-bit number. So the 16-bit number in the instruction field is treated, so here's my 16-bit field, so this is 16 bits. This is treated as a 2's complement number, which means, the high order bit here is, if you want to think of that, as the bit that tells us whether the number is positive or negative. If I'm going to convert that into a 32-bit number, how do I do that? Okay, and you can say, is there complicated logic? Turns out it's all just wires. There's nothing fancy here, but we do have to be a little careful about it. So if this number is positive, in other words, the higher order bit is 0, then the 32-bit representation is the same. We just copy over these low 15 bits, and in fact, we copy over that 0, like so. And then we want zeros all the way up in the high 16 bits. Right. So this 32-bit representation is the numeric equivalent. It represents the same integer as this positive number. Right. When this number is negative, what do we do with these high order bits? We make them all 1s. Okay. Because that would be the 32-bit representation of the same integer, right, with a high order bits all 1s. And so the reason it's called SXT is sign extension. This bit here basically gets copied not only to the 16th bit of the constant, but also bits 31 down to 16. So this is bits 15 down to 0, the bottom 16 bits. And so the high order 16 bits are basically the instruction field, number 15 replicated 16 times. So that's sort of the JSIM way of producing 16 bits of signal from or 16 copies of a particular signal. So that's what sign extension means.